We are the large-scale Lunar Prospector Rover team, and our goal was to design a rover to submit to the NASA Rascal competition, as well as create a scaled-down prototype for that design. This project was a great demonstration in the importance of prototyping as a part of space mission design to ensure the highest chance of success, despite a possible lack of knowledge on your targeted environment. And our team will explain the thought process behind it all over the course of this presentation. For the NASA Rascal competition, we were tasked with developing an innovative approach to a rover that could withstand the permanently shadowed regions of the lunar South Pole for a year-long prospecting mission in support of future Artemis endeavors. For our proposal, the Surface Yield of Lunar Volatiles Identification and Analysis Rover, or SYLVIA for short, our two major design considerations for this mission were the scientific instrumentation and the mobility system. However, our chosen spectrometers, sample collection system, and scientific camera suite would be rendered useless if Sylvia cannot navigate the harsh surface that could lie ahead as she delves into the target location of the Daguerreotype crater PSR. As our slogan goes, in the words of Nicholas Copernicus, Siccum umbra revelat, as the shadows reveal. Thus, our methodology beyond submitting the mission proposal was to develop a 1/4 scale prototype that would be solely focused on justifying the mobility system of choice for Sylvia's overall design. In order to do this, the possible terrain scenarios of the Daguerreotype crater had to be characterized to formulate our prototyping objectives. The mobility system needs to be capable of all of the following encounters that it could face beyond normal traversal across the lunar surface: navigating up and down slopes up to 44 degrees, climbing obstacles such as rocks up to 1 wheel width of diameter, and being able to unstuck itself from being submerged in powdery or icy regolith-like soil. Based on these testing objectives, the active rocker bogie design was our architecture of choice for the proposal, and I'll hand it off to Aiden to explain why this was the system that we used for Sylvia's prototype.
Traditional rocker bogie systems are characterized by two separate arms on each side of the robot, which are connected via a differential in order to reverse the angle of each arm. This type of suspension system is good at traversing small obstacles on one side of the rover, which can be up to twice the size of the wheel diameter, but is unable to change the chassis attitude while traversing downwards or upwards on a large slope, and thus provides difficulties when using the system in a lunar crater. In order to be equipped for the unknown terrain that might be found inside the craters of the lunar South Pole at the mission site, we want the system to be as capable as possible. In order to do this, we propose changing the traditional rocker bogie system to have active control via servo motor of each suspension arm. Our prototype decided to focus on the mobility aspect of our mission design, and thus neglects to include the prospecting and scientific instruments. This allowed us to create a suspension system mimicking Curiosity's geometry, which allows us to show that this active system provides benefits for off-the-shelf and previous designs of rocker bogie systems.
Having all of the aluminum tube and plate processed and prepared at the Engineering Design Center, we proceeded with the assembly process. This included TIG welding at ZeroCraft Makerspace with the help of Terry and various other methods including aerospace-grade 3M panel bond.
At the core of our power system lies a robust 11.1 volt 3S 10 amp hour lithium polymer battery. It was chosen for its high energy density and reliability amongst prototyping RC vehicles. Our dual channel switch, a critical component, ensures controlled power delivery and system safety. It's our first line of defense in power management and separates our brains, our computer and electronics, from our DC motors and servos. Sylvia's computational intelligence is powered by a Raspberry Pi, safeguarded by a 5-volt regulator. This setup provides a stable current, preventing voltage fluctuations that could disrupt mission-critical operations. The connection between the Raspberry Pi and the Arduino Mega is achieved through a direct serial USB connection. This enables a seamless transfer of intricate commands necessary for precision control. Taking a closer look at the Arduino acts as our microcontroller. It sends direct communication to the DC motors and servos via feedback loops and tells them what angle, direction, or speed they should be going. The Raspberry Pi serves as the brains, which tells the Arduino via the Xbox 360 controller exactly what input the user wants. Our servo system, integral for navigation, receives a finely regulated 6.4 volt supply. This powers 4 steering servos and 2 suspension servos, allowing for dynamic adjustment to the rover's orientation and ensuring optimal contact with the lunar surface at all times. The breadboard serves as the nerve center, linking the DC motors for symmetrical articulation. This arrangement guarantees that Sylvia maintains balanced propulsion and steering, enabling it to maneuver over uneven terrain without any issue. Despite being aerospace engineers, we ventured into the realm of electrical and computer engineering, transforming challenges into opportunities for innovation. Each wire, each line of code was a journey of discovery.
For the purposes of visual data as well as resource exploration and extraction from the lunar surface, the Sylvia rover will have a robotic arm from the MyCobot series by Elephant Robotics. This is a MyCobot 280 Pi which has a built-in Raspberry Pi at the base that is customized to explore the lunar surface using visual data with a set of autonomous commands and an API that ensures a safe and efficient examination of high-priority resources like water, aluminum, iron, titanium, silica, and platinum. The arm has 6 degrees of freedom. The tip of the arm, which is referred to as the atom, has a GoPro 9 attached to it for the prototype design. The idea is to be able to swap the tools on the atom with a gripper or a suction pump for resource extraction. The code that makes the arm pan the lunar terrain is written using Python and runs in Visual Studio Code. The 5x5 RGB LED display can be developed to match a certain color corresponding to the tool attached to the tip of the arm.
With the prototype fully assembled and able to conquer the 3 major terrain scenarios in a controlled environment, next steps would be to complete more rigorous testing to find its points of failures and ultimately validate the mobility system. As for future testing and analysis, one of the best analog sites for lunar rover testing is right in our backyard, Cinder Lakes Crater Field in Flagstaff, Arizona. By demonstrating this unique system on the same testing grounds that were used for the Apollo lunar buggy, this would give us much more confidence that this design can be proceeded with for the overall mission, and the scientific testing and integration teams can feel reassured that their system will be safe for operation. This project has helped us learn a lot about engineering processing and maintaining ethical protocols throughout design, integration, and testing of each system. Special thanks to NASA, Zerocraft Makerspace, University of Arizona's Engineering Design Center, and the Asteroids Lab for your contributions.